Our last unit has to do with linear and exponential functions. Just a few definitions and not really a whole lot to worry about here with the final looming. You want to be able to tell that the dependent variable is your y and the independent variable is your x. Other than that, essentially what we're trying to say is we're going to take real life situations and we're going to try to model them. The model is typically called a function. There's three ways that you can represent a model. You can use a graph, you can use a data table, and you can use an equation. We're going to take one look at a graph, one look at a data table, and then the rest of the time we'll spend looking at equations. A couple more vocabulary words that we need when we're looking for how to describe a graph or how to describe a table of values is domain and range. The x is the independent variable, but the x values that you use for the independent variable, those numbers are called the domain. The actual numbers you use for the y variable, those are called the range. So here, when we look at an actual graph, this part of this is going to remind us of section 5 in the last unit. Your independent variable, that's your x. You literally look at your x-axis. Your independent variable is age. Your dependent variable, that's whatever's on your y-axis. Your dependent variable is going to be your weight. Now the domain and the range, that's where you have to actually look at the picture and figure out what numbers were used. The domain is asking you what x values did you use. So if I look at the graph, left to right is my x's. So if I go to the very left, the lowest x value that got graphed was 0. If I follow the graph to the right, the highest x value that got graphed was at 40. And because the graph is a continuous line, all my dots are connected, it's just everything from 0 to 40 I can find an x value that's been used. The range is the y values. Now you want to go from lowest to highest, so you want to look at the graph from bottom to top. The lowest y value that got graphed looks to be about 10. The highest that the graph reached was about 130. And again, we touched every y value in between because we have graphed it with a solid line. From a table, all you really need to remember is that it's quite standard. X's, then y's. So your independent variable is going to be altitude. Then your dependent variable is the boiling point of water. Your lowest altitude was 0, that's sea level. Your highest altitude was 9,000. Now if we made a graph, we would actually connect all these dots as we went along. The boiling point of water goes down. We would connect those dots because in between we wouldn't expect anything funny to happen. We wouldn't expect all of a sudden here the boiling point of water shot up skyward for some reason. The range, you want to go from lowest to highest, so make sure you're looking at your numbers. The lowest number is 193.6. and the highest number is 212. Remember, your test is going to be multiple choice. If I had those listed backwards, that is not the best choice. Even though it's correct, it's not the best. And your instructions will tell you to circle the best answer. So don't get like lazy-minded. Now the rest of this we're going to talk about actually writing formulas for the functions. We're going to talk about linear functions first, which means the graph would make a straight line. Now just because it would make a straight line doesn't mean we're going to actually graph anything. We're not. Oops, sorry about that. My pen got away from me. Instead, we're going to use the formulas for, in this case, a line, and use that to help us write a model for different situations. Y equals mx plus b is the linear formula we're going to use. M is the slope, but M meaning the slope, it tells you how much a line slants. If I'm not graphing a line, I don't really care about the slant. So in our context, it's still M, it's still the slant, but in our problems, we're going to be considering a rate of change. Something in the problem is changing, and this tells us how much. B was our y-intercept. Well, again, I don't need a y-intercept if I'm not making a graph. So instead of a y-intercept, B is going to be our starting value for whatever the problem is talking about. So here we go. I know this is going to be a linear function right now. So I know I want to fit into y equals mx plus b. So I read the problem. A new computer costs $1,500 today and decreases in value at a constant rate of $300 per year. That's the part I use to write my linear function. One of those is telling me a rate of change. First of all, it's telling me my change is negative. If something is decreasing, that's negative. So if I'm decreasing at a rate of $300 per year, my rate of change is negative 300. Now that part just fills in for the x, so the x is still there. The x remains part of the formula. Now it decreases by $300 a year, starting from what amount? And that would be the 1,500. This is your function. Now if you actually want to answer the question, which will be a separate question, what will the value of the computer be in 2.5 years? You take that 2.5 and you plug it in where x is. So in your calculator, you do 300 times 2.5 plus 1,500. And that'll give me an answer of $750. Now the next one, talking about the cruise ship, works exactly the same way. Exactly the same way. So the best thing you could do with the final exam looming is pause this recording right now and do the next one, and then just check your answer. Increases at a rate of 60 is y equals 60x, and we're starting at 1,200. Now if I want to see how much the cruise will cost in 4.5 years, I just do the part after the y equals 60 times 4.5 plus 1,200. And that means in 4.5 years, the same cruise should cost me about $1,470. Now in this one works the same again, except it gets a little tricky when we start talking about finding the new world record. So again, I would pause the recording, make sure you can get your formula, and then check and see what you did, what you were supposed to do. So the world record is falling, so that means your rate of change is negative 0.05, keep the x, and it's falling from 50/40. Now, when we want to go and solve it, we don't plug 2020 in because it falls at a rate of 5 seconds per year, which means that if I plug in 2020 for x, that's 2020 years later. So I need to do a little math over here. 2020 is how many years after 2006? And that's 14. So if I want to know what the new world record would be, I'm wanting to know 14 years later. And that would be 49.7 seconds. Now here we get a little bit fancier. Here we're going to have to actually find our own rate of change. Now we're going to make data points, and if you'd like to use the slope formula, I've put it on your formula sheet for you. If you remember your algebra class, and it's quite friendly in your mind, it's all right. I just try to avoid formulas that don't necessarily mean anything. I'd rather you kind of understand a pattern. So basically we're going to get two pieces of data that are linked. I have a dog that weighed 2.5 pounds at birth, and then it weighed 15 pounds after 1 year old. Now I want to eventually be able to predict my dog's weight at a certain age. If I'm wanting to predict weight, weight is the variable that would be like the dependent variable, and age would be independent. So what that means, if age is the independent variable, that's your X, weight is your Y. So if I want to make an ordered pair out of a 2.5 pound dog at birth, his age would be 0 and his weight would be 2.5. If you weighed 15 pounds at a year old, that's 1 year old, 15 pounds. We want to look at our weights. I'm wanting to find a rate of change for my weight. Well, if it was 2.5 and it went to 15, how much did my weight change? Well, it changed by 12.5 pounds, and it did increase by 12.5 pounds, so that makes it positive. But the second half of this is you're always going to go over what period of time. So he gained 12.5 pounds over 1 year, which as a fraction just reduces to 12.5. So I can write my model as y equals 12.5 x plus his original weight was 2.5. Now if I want to see how much the dog weighs at 5 years, I come over here and I do 12.5 times 5 plus 2.5 would equal 65 pounds. And at 10 years old, and this is comment on the validity of the model. That's because we did everything right, but the problem doesn't make any sense. If you've got a puppy that weighs 2.5 pounds when it's born and it is only 15 pounds at 1 year old, that's a small or a skinny dog. When it's 5 years old, if your 15-pound dog has gained 50 pounds in 5 years, you're feeding it wrong. And then at 10 years, if it's 127.5 pounds, well, that dog is probably dead because its blood won't move anymore. It can't move anymore. Because this whole assumption is when you have a rate of change, you're assuming a constant rate of change. In this particular example, we're saying that a dog that gains 12.5 pounds in its first year is going to continue gaining 12.5 pounds every year. When that's not true. The rate that a puppy is going to grow is going to be huge that first year, but then it's going to level off very soon after 1 year. So we're going to have a whole lot of growth that first year, and then we shouldn't have a whole lot of weight change afterward, unless there's something seriously wrong. So just because we can do a linear function doesn't mean we should. Not everything is going to follow a linear pattern. This will, and it works just like the previous one, except it doesn't get ridiculous. So, again, I would advise you pause this and then look back at the work after you're finished. A new stereo cost $800. A 2-year-old stereo is worth $300. I'm looking for my rate of change. The value of my stereo went down $500. It went down $500 over 2 years. So my rate of change is negative 250. So my formula becomes y equals negative 250x plus 800. Now if I want to find out how much the stereo will be worth in 6 months, you don't plug in 6. It'd be negative 250 times a half. 6 months is a half of a year. And we talked about how much the stereo would depreciate per year. Plus 800. So if I do that, I find out that my 6-month-old stereo is now worth $675. The next one, this is essentially the same thing, except we have to deal with the years again. We don't deal with the years, not really, until we get to the point where we're ready to plug in. So it would be a good idea to pause this a moment and see if you can get your ordered pairs, find your rate of change, and write your formula. Even finish it if you feel like it, and then check your answer. In 1930, the world record was 46.8. In 1970, it was 43.8. I want to know how much the record changed. So from here to here, it went down 3 seconds. It went down by 3 seconds over what period of time? From 1930 to 1970 is 40 years. Did a little arithmetic in my calculator, and my rate of change is negative 0.075. To write my formula, my rate of change times x plus the original record. Now, the question is, what do I want the record to be in 2016? Again, we can't put in 2016. You need to do 2016, the difference between that and whatever year that came from. That came from 1930. So that's a difference of 86 years. So if I want to find the record for 2016, I plug in 80. Plug in 86. And that record would be 40.35 seconds. Now the next one, except for the word millions, works exactly the same way. Like I said, I encourage you to try that one on your own. It's the last one of the linear functions, and the rest is exponential. In 1986, the amount contributed to political action groups was 32.7 million. In 1992, it was 178.6 million. If I want to find my rate of change, from here to here, I contributed more, so it's going to be positive. If I do 178.6 minus 132.7, I get 45.9. Over how many years? That'd be 6, which as a decimal is 7.65. That's my rate of change. And what I started from was 132.7, knowing that it's millions. 2020, I need to know how many years 2020 is past 1986. If I do that subtraction, I get 34. So if I want to estimate how much was given to political action groups, in 2020, or how much will be given in 2020, I'm a little ahead of myself, that would be 392.8, and don't forget we were talking about millions there. Well, we had two growth patterns we wanted to talk about. Well, growth or actually decay. Linear. The linear is what we've been talking about. Y equals mx plus b. If we want to talk about exponential growth, here's our new formula. Now, with exponential growth, you're going to change by a certain percentage. So it's going to be very obvious the difference. P, that's going to be like our B over here. That's going to be our original value, our starting value. R is our rate of change, only this time it's a percentage. You want to make sure you change that to a decimal. Price of milk has been rising with inflation at 3% per year. Notice, that's a slap in your face, obvious difference from what we've been doing. Now, if you're just asked to write the formula, which you usually are at first, we're going to fill in for the P and the R. That exponent that's a T just stays for the formula. That's what we plug in to solve for the answer for the second part. P, that's the original price, in this case of milk, was $2. The price is rising at 3%, so this is 1 plus 0.03 because I have to change 3% to a decimal. Now, the answer is multiple choice, but hopefully you would never want to leave that way. 1 plus 0.03 is just 1.03. which makes everybody's life easier. So this is the formula. That's the function. Now, if you want to find out how much it is 3 years after it was $2, then we're going to plug in 3 for our exponent. On your calculator, you want to type this in just the way it sits. Now, if I need an exponent of 3 on my calculator, it's not going to look that way. I use my caret key, which is right below my arrows, and then my 3. And that raises that to the third power, which makes this, I believe, $2.19, if I recall. Yeah, there it is. The difference here, this price has been falling by 25%. It's still a percentage, so it's still exponential. But the difference is, and I should have said it or wrote it this way, if your rate of change is negative, you actually want to subtract. So it's plus R if it's increasing, it's minus R if it's decreasing. So if the price starts out at $200, and it's falling by 25%, that's 1 minus 0.25. Which again, hopefully you would never dream of leaving that way. 1 minus 0.25 is 0.75. That's the function. If I want to know what it can be in 2 years, then I just use 2 for my exponent, which I can do that by just hitting the x squared key. We'll put a little squared up there. Or I can continue to use my caret key. Either way, this answer is going to turn out to be $112.50. This one's a good one for you to try on your own because the next exponentials we do get kind of special. My initial value is 55,000. I'm increasing at 22% a year, so 1 plus 22% is 1.22. That's my function. If I want to know what that's going to be in 5 years, I definitely want to use my caret here with a 5, and that's going to be a bunch of people. 148,649. round it off to the nearest human because we don't count humans as tenths or hundredths or anything like that. Here we're going to start the section on doubling. Doubling is exponential, but it's just sort of a special exponential. So before we talk about the specific problem here, let's just look at the formula for a second. Doubling means that we are increasing by a certain percentage, otherwise it wouldn't be an exponential function. If you double something, by what percentage are you increasing it? When you double something, you actually increase it by 100%. 100% as a decimal is just a 1. So anytime we're talking about doubling, instead of 1 plus r, the 1 plus r just becomes a 2, because doubling is always plus 100%. Now, that's not all the adjustments we have to make. This is our let's learn it how to do it problem. Let's fill in some of the stuff that we know. My original value is this 300 gigabytes. And I'm going to have a 2. Now usually in these doubling ones they don't ask you to find the formula, they just ask you to figure it out. So here's the thing, it doubles every 2 years and I want to know what it will be in 6 years. Normally I would just use 6 as my t, but it doesn't double every year for 6 years. So I've got to figure out, my exponent has got to be how many times it doubles. In 6 years, doubles. In 6 years, if it doubles every 2 years, I need to divide. Because in 6 years it's only going to double 3 times. So the way the formula looks, the t still is how many years, but then you divide that by capital T, which is your doubling years. How long does it take for whatever it is to double? Now to work the problem, you just type it in the calculator the way we've been talking about. 300 times 2 exponent of 3 gives us 2400 gigabytes. So we kind of know the formula. Let's try it again without having to go through all the thought. Your bank account has a doubling time of 13 years. How much money would you have in an account after 50 years if your initial deposit was $1,000? So, initial deposit comes first. Doubling means 2. The number of years you're talking about in the problem goes on top. You divide that by your doubling time. Now that's a nasty mess. If you even pick up the calculator and do 50 divided by 13, that doesn't even turn out to be a nice decimal. So don't do it separately. On your calculator, we're going to type in the first part exactly like we're used to, and then the caret. If your exponent is a fraction, just enclose the fraction in another set of parentheses. Then you don't have to do any rounding, and you don't have to worry about possibly making a mistake. Just make sure you got the right one on top and the right one on the bottom. This turns out to be $14,381.62 when you round. The last two, this problem and one more, I would encourage you to try it on your own. Let me just say, let's use this as our original value. It will make our life easier. We're told we have a doubling time of 40 years, and then we're given way too much information. If we use the 6 as our original value, and we're doubling, then when I go to write my fraction to figure out what the population will be in 2030, I don't have to do some math off to the side to figure out how many years is that later, because 2030 is 30 years after the year 2000. Now the advantage to that should be obvious now. If I had used 3 billion, I would have to figure out the difference between 1960 and 2030. I'd have to do some more scratch work off to the side. Nothing wrong with that. Should actually give you the same answer as long as you don't round stuff off. It's just I could do the 2000 in my head. So on my calculator again, I want to make sure that if my exponent is a fraction, I put it in parentheses. And this gives me 10.1, which is billions of people. In 2200, that's 200 years later, with a doubling time of 40 years. All you got to do is make sure you get that fraction right side up, not upside down. The number of years you're talking about divided by your doubling time. Yeah, I made a boo-boo up above. Writing too fast. Now there's absolutely nothing funky about the last one. I highly encourage you to do that one on your own and use me to check your answer. $74,000 is my original amount. Doubling every 25 years. I'm looking for 125 years. On my calculator, 74,000, 2 in parentheses, and my exponent enclosed in another set of parentheses. And that's it.